Okay, welcome back. This is a continuation of lecture 5. So here we'll be discussing operating system operations. That is how an operating system works. Basically, operating system is interrupt driven. Okay, that is interrupt based on the interrupt the operating system works. If there is no user program, or if there is no IO operation, or if there is no user inputs currently available, then the processor will be idle and operating system also will be idle. Okay. If there is a user input, or if there is a demand for IO operation, in that case that will be signaled to the CPU through the operating system by interrupts. If any hardware device needs attention, then it will create a hardware interrupt. If any user program or process needs CPU's attention, then it creates software interrupts, which we have already discussed. Sometimes interrupts may also get created if a process is running for a long period of time. So any process should stop at one point of time. If it is not stopping, then it unnecessarily takes the CPU time, and CPU time will be get wasted then. So to avoid that, operating system will keep checking if any process is running beyond the time limit. So it may happen because of an infinite loop, or it may happen because of just keep on waiting for an IO device. In such cases, also the operating system will create an interrupt, and that particular process will be stopped. Okay. So the operating system allows the programs to run in two modes. Okay, there are two modes possible for a particular program to execute. One is called as user mode, the other one is called as kernel mode. The user mode is a restricted mode. User mode is a restricted mode where the program is allowed to execute only a few instructions which will not create any threat for the computer. Okay. Whereas kernel mode is a highly privileged mode where the program can execute any instruction, but it also involves some risk. So the kernel mode will not be normally given to a particular user unless and until it is acknowledged by the operating system. Okay. So how to control the two modes? The two modes can be controlled by using a mode bit. So initially when a particular process is loaded into the main memory, so initially you are loading the process from the hard disk to main memory. Okay, at that time the process will be in kernel mode. At that time the process will be in kernel mode. Once the process got, so it is loaded from the hard disk. So let us assume here is the hard disk and the program is residing in the hard disk. Okay, so somebody should load the program from the hard disk to the main memory. Who will do that? User will not do that, operating system will do that. And this is what mode? This is kernel mode. So operating system will load the program from the hard disk to the main memory. So at that time it will be in kernel mode. Once it is loaded, the program will continue working in user mode. Okay, and during execution, assume the program wants to perform some high privileged task for which it needs the support of the operating system. Okay, that is, it needs to access a particular hardware. So it cannot do directly. So it will call the appropriate system call. So system call or functions which are used to perform high privilege task. So there are different system calls available to perform different operation. Maybe there is a system call to perform write operation on the memory. Maybe there is another system call to perform read operation from the memory. There may be a system call to perform printing to the printer. Like that, for different operation, there will be different system call. So the user program, whenever it wants to perform high privileged task, then it will execute the appropriate system call. Once the appropriate system call is being executed, the control will be transferred to the appropriate routine in the kernel. Now the program is in the kernel mode. It is not in the user mode. Okay. And the system call will be executed by the operating system. Okay. So once that is done, once the particular system call is executed, again the control will be given to the user. Okay, now the user will continue executing the program in user mode. Okay, so here user mode is represented with the with a value 1. So we use something called mode bit. If the mode bit is 1, it means it is user mode and the user program is getting executed. If the mode bit is 0, it means it is kernel mode and the kernel program and the operating system is executing that particular process. Okay, I think the thing is clear. It is clear. So initially, when you load any particular process or a program, it will be in the kernel mode. That is, it will be loaded by the operating system. The control will be with the operating system. Once it is loaded, the control will be given to the user program. User can execute some limited set of instructions and he will perform the task. Whenever a user want to perform a high privileged task, he will call the appropriate system call and the control will be given to the operating system. So the mode will be changed from user mode to kernel mode. Now the kernel will execute that particular system call and again it will give the control back to the user mode. Okay, so during kernel mode the mode bit will be 0 and during user mode the mode bit will be 1. Okay, so why we are doing like this? We are doing like this to ensure safety. If you allow user process to execute kernel operation, then it may lead to some unpleasant things. Like if there are more than one process in the memory, maybe if one process is getting affected, it may affect another process also, or it may affect the operating system itself. To avoid such things, the uh, to avoid such things, operating system supports two modes. So if at all, if there is any issue or any problem with a particular process, it should affect only that process. It should not affect any other process. Okay. So with that intention, uh, a particular operating system allows multiple modes of operation. So generally a computer operating system supports dual mode. Okay, there are sometimes a computer may also support multi-mode operations, that is it may have more than two modes also. So it is not that it is restricted to two modes. It can have more than two modes also. Assume a typical computer which is running a software called Virtual Machine Manager. So what is a virtual machine? Virtual machine means it is like a simulated or a virtual environment. Say for example, I am using Windows operating system. Now I can have a virtual machine for Linux. Okay. So if I execute that particular program, I will get the look and feel of the Linux environment. And that particular program will be controlled by a software, and that software is called as Virtual Machine Manager. So if your computer is having a Virtual Machine Manager, then the user program will have the least privileged, the user mode. Then your program, then your system will have three modes: user mode, the first one, and then it will have the next mode for virtual machine and next mode for kernel. Okay, so user mode will have one level of privilege, and when you are running virtual machine, it will have higher privilege than the user mode. Okay, when kernel is being executed, kernel will have higher privilege than the virtual machine. Okay, So like that, depending on the type of the system, it may have more than 2 modes also. So it is highly recommended to have at least 2 modes. So nowadays, most of the operating system has these 2 modes, user mode and kernel mode. Okay, so this is done to ensure safety. Fine. So the next thing what we'll be discussing is, and also uh, timer. Timer is an important concept which is used by the operating system to avoid any infinite loop or a process which is waiting for an IO device for a for an unlimited time or for a long period of time. Okay. So what happens in the sense, the operating system may maintain a timer. Okay, and it may keep some value in the timer. Assume that a particular operating system is starting a particular process P1. Operating system is starting a process P1. Let us assume this is process P1. And while starting the process P1, the operating system understands that maximum this process may take, uh, say, this process may take 5000 milliseconds to complete its execution. It should not take more than 5000 milliseconds. Then what it will do in the sense, it will set a timer. It will set a timer, and probably here it will put a value, say 6000. It will put a value 6000, and this value it will decrement for every 1 millisecond. Every 1 millisecond this value will be decremented. Okay, so if it, as long as it is zero, as long as it does not become zero, this process will kept in the main memory, and the processor will be given a chance to execute this particular process. If it becomes a negative number, then it means that it is taking more time, because it is expected to complete within 5000 milliseconds, but now it has become 6000 milliseconds. So now the operating system will understand that most probably this process has get into some problem, like infinite loop, or it is keep on waiting for an IO device. So in such cases, the operating system will create an interrupt. It will create an interrupt to the CPU, stating that that particular process is taking a long time. Okay, so it is up to the operating system. If operating system feels it may give some more time, instead of 6K, okay, it may give another 1000 milliseconds. But still, if it feels that no, it's really something going wrong, then it will create an interrupt to the CPU uh, to stop that particular process and remove it from the memory. Okay, but it will maintain some log report. So in the log report, it will be mentioned like why the process was moved from the main memory. So by seeing that, the user can understand. Okay, so this is how the timer works, right? So let us now discuss some examples for this timer. Okay, a 10-bit uh, so a timer will also use a counter. Let us discuss this with an example. A 10-bit counter with 1 millisecond clock allows interrupts at intervals from 1 millisecond to 1024 milliseconds in steps of 1 millisecond. What does it mean? A 10-bit counter with 1 millisecond clock allows interrupts at intervals from 1 milliseconds to 1024 milliseconds in steps of 1 millisecond. So you have a counter. Okay, the size of the counter is 10 bits. The size of the counter is 10 bits. That is, it can hold 10 values. Okay, each bit is what? A bit is a basic unit of data storage. So each bit can be either 0 or 1. So basically it can have 10 bits. So each of these can be 0 or 1. So what is the minimum value it can store? The minimum value is all these will be 0. Okay, all these 10 bits are 0. That is the minimum value. And what is the maximum value? All these 10 bits are 1. That is the maximum value. Okay, so if all the 10 bits are 0, then what it means? If all the 10 bits are 0, then then the value is 0. If all the 10 bits are 1, then the value is how much? 1023. Then the value is 1023. Okay. So totally using a 10-bit counter, how many values you can store? You can store values from 0 to 1023. Okay, so that means you can store 1024 values totally. Totally you can store 1024 values. Okay, so this counter can be used to create an interrupt in the range of 1 millisecond to 1000 millisecond, 1024 milliseconds. Okay, it means that it means that so the minimum value it can store is 1000 and the maximum value it can store is 1023, which means it can be used to create an interrupt in the interval of 1 millisecond to 1024 millisecond. If you want to create an interrupt after 1 millisecond, then just store 0 here. Just store 0 here. Then you have a clock which ticks for every 1 millisecond and at the step of 1 millisecond. So after 1 millisecond, it will be decremented. It will become negative value. Then the operating system will create an interrupt to the CPU. Okay. If you want to create an interrupt after 5 milliseconds, then store 5 here. Okay. So 5 means what? 5 means what is the binary equivalent of 5? So 5 means yeah, 1 0 okay, so 0 8421, right? 0101. So this is 5. So the last 4 digit, that is the least significant bit, will be 0101. Remaining all bits will be 0. Okay. So 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 here what will happen? You are storing 5. So after 1 millisecond, this will become 4. After that is sorry after 1 millisecond it will become 4, after 2 millisecond it will become 3, after 3 millisecond it will become 2. Okay, after 4 milliseconds it will become 1, after 5 milliseconds it will become 0, after 6 milliseconds it will become -1. Then it will create an interrupt because the time has elapsed. Okay, if you want to create an interrupt after 1024 milliseconds, then fill it all with ones and decrement the counter. Okay, so that's the idea, right? So similarly, you can work out. Okay, say uh, if the counter size is 8-bit, then it will have 0 to 2 to the power 8. Then it can hold. Uh, it can be used to create interrupts in the interval of 1 milliseconds to 2 to the power 8 millisecond. Okay, this is 2 to the power 10. Okay, so that is the whole idea. Here is another example. A program with a 7-minute time limit, for example, would have it counter initialized to 420. Every second the timer interrupts and the counter is decremented by 1. So this is a very straightforward example. Uh, so the program with a 7-minute time limit, that is the operating system identified that this program should maximum take 7 minutes to execute. It should not take more than 7 minutes at any cost. Okay. So in the counter, it stores a value 420. Why 420? Because 7 minute contains 420 seconds, 60 into 7. Okay. So it stores the value 420, and what it does is after every second it will decrement this. After 1 second it will become 419. After 2 seconds it will become 418. Okay, and whenever it becomes a negative number, whenever it becomes -1, then the operating system will understand that it is taking too much time, so something wrong, maybe an infinite loop, or it is waiting for an IO operation to complete. So it will immediately create an interrupt to the CPU and it will request the CPU to halt that particular job. Okay. So this is a very humanly example, but in case of a computer, the computer clock will not tick in terms of second. Rather, it will tick in terms of millisecond, nanosecond in at that rate. Okay, fine. So that's it for this session. So let us stop here. So what we have understood in the sense, basically operating system is interrupt driven, and operating system can work in multiple modes. Normally it works in two modes, user mode and a kernel mode. With user mode, the control will be with the user, but the user will have a restricted instruction set which he can execute, whereas the kernel mode is a highly privileged mode. If user mode want to execute some high privileged instructions, then he has to call the appropriate system call, and it will be transferred from user mode to kernel mode, and operating system will take charge and it will execute the appropriate routine, and once again the operating system will give the control back to the user mode, uh, and, and this is how the things works. So user mode is represented by the mode bit 1, and kernel mode is represented by the mode bit 0. In some cases you can also have more than two modes, multi-mode. Example, we have discussed a VMware. If your computer is running a VMware, then VMware will have a privilege which is in between user mode and kernel mode. That is, user mode will have the limited privilege, and the VMware will have better privilege than user mode, and kernel mode will be highly privileged. And then we have discussed about timers and counters. So basically, timers are used to ensure that no program is running for a long period of time and and unnecessarily using the system resources. So operating system will ensure that by using timers and counters. Okay, thank you. Thanks for joining. We'll stop here.